In this video, we're going to look at the inverses of circular functions. All right, now if a function is one-to-one, then it has an inverse function. Okay, now one-to-one, I think of sine x. All right, we can plot it something like this. Okay, now there's a way we can tell if something is a function, and there is, of course, and the way we can do that is we can use the vertical line test, and that means wherever we draw a vertical line on the graph, it will cut the graph at one place only. All right, that doesn't happen, for instance, with a circle. Okay, a circle is a relation, not a function. A vertical line test cuts it at 2 points. Okay, so with sine x here, we see that a vertical line test anywhere crosses the function at 1 point only, but that doesn't mean it has an inverse. In this case, we have many x values mapping to a single y value. Okay, and what we need is something that is one-to-one. So there is one value in the domain mapped to exactly one value in the codomain or the range, and vice versa. There, for every value in the codomain, the inverse mapping takes it back to a single exact value in the domain. Okay, so that must work both ways. And so one-to-one, all right, the sine function then over some open interval there is not one-to-one. But we can restrict its domain, and when we restrict its domain, we can create something that is one-to-one. All right. And if we take, for instance, f is a map that maps the closed interval minus pi on 2 to pi on 2 into the codomain closed interval minus 1 to 1, where f of x is sine x, then we have this sketch here. That is y equals sine x on the restricted domain. And now here it becomes one-to-one. And just another quick test, just as a vertical line test can tell us if something is a function or not, then something called the horizontal line test can tell us if something is a one-to-one function and therefore has an inverse. So if the horizontal line test is simply draw a horizontal line anywhere on the object, on the graph, and if it crosses at 1 point only, then we have a one-to-one function. I might just get rid of that. Okay, now, so in this video, I want to look at inverses of the trigonometric functions. Okay, so having done that, let's just move this down a bit. Having done that, we've restricted our interval to the closed interval minus pi on 2 to pi on 2. So here we are, minus pi on 2 to pi on 2. And over that interval, we can see that it's one-to-one. A horizontal line test will verify that for us. And so that means it has an inverse. Okay, and that inverse then is the map that goes from the codomain, back to the domain. Okay, so the domain of the inverse is just the codomain of the original map f. All right, so that map goes back the other way, and we write that f inverse of x as inverse sine of x. Okay, and when we plot that, we end up with this sketch here on the right. Well, it's not a plot, it's a sketch. We end up with a sketch graph on the right here, y equals inverse sine x. And in our case now, the domain is -1, the closed interval minus 1 to 1, and the codomain or the image or the range is minus pi on 2 to pi on 2, again a closed interval. All right, and these are just reflections about each other of the line y. These are reflections. If I reflect the here y equals sine x about the line y equals x, like that diagonal line there, I'll get this, the graph of the inverse. Okay, so that's how we find that. Similarly for cosine x, the original map, if we restrict the interval from 0 to pi, the codomain or the image is the closed interval minus 1 to 1, where f of x is cos x, and then the inverse of that is now reversed. the codomain of the map F becomes the domain of the inverse map, and we go back to the original domain, okay, where F inverse of X is inverse cos X. Similarly for tan X, if we restrict it, for instance, to the interval minus pi on 2 to pi on 2, that then maps to the reals, where f of x is tan x. We've seen that graph, has each of those branches every period of pi. From minus pi on 2 to pi on 2 is one branch, and then from pi on 2 to 3 pi on 2 is the second branch, and so on. And also back in the negative direction as well. And we've seen that in previous videos. So the inverse becomes here, it becomes a map from the reals to the closed interval minus pi on 2 to pi on 2, where f inverse of x is inverse tan of x. Now graphically, the inverses of sin x, cos x, and tan x are reflections of these graphs about the line y equals x. So having done that, we've defined what the inverses are and what we mean by inverse. This one-to-one mapping that is an inverse is also known as a bijection. Technically is known as a bijection or bijective, a bijective map. Okay, now, but what if we want to find the inverse on a different domain? Let's say we're restricted to a different interval. I started in the video above by choosing the interval from minus pi on 2 to plus pi on 2. But what if I wanted to map, say, the interval from pi on 2 to 3 pi on 2 and find the inverse for that? Because if I just consider this part here, this right-hand branch here, in this interval from pi on 2 to 3 pi on 2, that's also one-to-one. You could easily quickly verify that with a horizontal line test. If I restrict my function to that interval, pi on 2 to 3 pi on 2, okay, the map then gives me the codomain of the closed interval minus 1 to 1, where f of x is sin x. So this is a different mapping. All right, this is a different function because it's defined on a different domain. All right, what would be the inverse of that? And we can also find that as well. So let's have a look at that. Okay, so here we are. So let's take that part of the graph of y equals sin x we were looking at on the previous page, over the interval minus pi on 2 to pi on 2, and move it right by pi units. And then what we'll do is we'll reflect it about the line x equals pi. So okay, so what we're going to do is take y equals sin x, and we're going to shift it right by pi units, so it's x minus pi. So the interval that was here, okay, that did go from here to here. Remember this one like that. We're going to shift that right by pi units. So here's the dotted line, okay. And now if we reflect that about the line pi equals x, so the filled in branch there reflected about the line pi equals x gives us this interval here, okay, and this becomes y equals sine of x minus pi, okay. And if I reflect it about the line, so I'm taking the negative of the inside the parenthesis, negative here, so I get sine of pi minus x. Okay, let's say now we wanted to find, okay, so this bit here is sine of pi minus x, okay, and this dotted one is sine of x minus pi, which was just simply sine x, this bit here, shifted pi units right, okay, from the origin here, shifted to pi units, okay, reflected about, and then what we've got by reflecting it, by putting the minus in here, minus parentheses x minus pi gives us sine of pi minus x, is what we've got is this right hand bit here that we're interested in. We've now got this. Okay, now let's find the inverse of that. Okay, all right, so here, so let's now find the inverse of y equals sine pi minus x on this interval pi on 2 to 3 pi on 2. Okay, so what we do, the process here is we set y equals sine pi minus x, and then simply swap the x and y, because remember we talked about reflections about the line y equals x. Okay, that still holds. That's how we're going to find the inverse. Because it's one-to-one, we're going to swap the domain and the codomain. Okay, so we're left with x equals sine pi minus y. Inverse sine of x on both sides. Inverse sine here, sine cancels, pi minus y. And what we have is inverse sine of x is pi minus y. And then what we're going to do is transpose the y onto the left-hand side and transpose the inverse sine x onto the right-hand side. And what we get is our inverse becomes y equals pi minus inverse sine x. Or if you like, probably more correctly, we should put f negative 1. It's not the power of negative 1, it's just negative 1 to indicate the inverse. So the inverse of x, f inverse of x, is pi minus inverse sine of x for pi on 2, 3 pi on 2. Okay, now the plot of this is going to look different. Okay, we've taken this transformed interval, okay, and we're now going to plot it. The way to think about it is that here's our interval. If I now were to reflect that about the line y equals x, this will reflect up here somewhere. Okay, and you'll see that shortly when I show you. Okay, so the inverse function, the inverse map, pi minus inverse sine inverse of x for pi on 2, 3 pi on 2 becomes the map f inverse of x, which takes a closed interval minus 1 to 1 to the closed interval pi on 2, 3 pi on 2, where f inverse of x is pi minus inverse sine x. Let's have a look at some plots of these to see what happens, okay, particularly this. Right? So here we go. Here's, first to start off with, good old function y equals sine x is this plot here. Okay, and then over the closed interval minus pi on 2 to pi on 2, the inverse is this other one in here. Okay, it's sort of in there. Okay, I haven't quite gone all the way to the intervals there with the plot, but anyway, and sine x is the bit left over. Okay, so that's the inverse. So what would the inverse of the transform one look like? Remember that one, pi minus x? Okay, let's have a look at that. Okay, so we've got sine of pi minus x is this one here. That's that one. Okay, and then the inverse, remember if we took this interval here, from there to there, and reflected it about the line y equals x, we end up with this object over here. Okay, and that is our inverse. And that is pi minus inverse sine x. Pi minus inverse sine x. Okay, that's the way to look at that one. Okay, that's it. Done.